Welcome to a discussion with Reshmi Ghosh regarding a LLM Capture-the-Flag competition that was hosted in order to better understand how we can safeguard our large language models from adversarial attacks from different parties. I hope you enjoy the discussion. That the competition that you hosted was between December and March, I believe.
Yeah, so I think just to correct this, we didn't host, I and the participants that you see from Microsoft, we were like a team that was participating in the competition. Eduardo, like the first three authors in the paper, Javier and Daniel, they were like the hosts of the competition. We won the competition in the second round, so second place, sorry. So that's the setup, and then we thought that it's a good thing to write this paper together and submit it to NeurIPS, as well as release the data set on Hugging Face. So that's the construct.
Okay, congratulations then. I guess I should say that in the beginning. But cool. Can we talk a little bit about the ambition for setting up the competition, like what the context is regarding this? Because my understanding is there have been some competitions of a similar nature before, but none that are quite one-to-one aligned with this one. So maybe if you could highlight what the competition was actually about, just for people that haven't read the paper, and then we go into more details.
Sure. So I think the competition was I would say an approach to get more insights into how different people around the world who are either security researchers or interested in security breaches, are interested in ethical hacking, are thinking about AI related safety or large language models related safety. And this is, I would say, an upcoming topic because up until now, jailbreak as a term was conventionally known in a lot of security scenarios. You could jailbreak a device, you could jailbreak a software system, take control over it, manipulate it, do things according to what you would want, right? And that's a method that is used by a lot of adversarial hackers and users around the globe to break into other systems. But the thing with large language models, or AI, as a lot of people call it, or even multimodal large language models, is the fact that these are brittle towards the prompts that they receive and consume and then reason on it, right? And that's because it's trained on different sorts of data. We don't really know about the explicit behavior or the nature of these models, given that some of these models are proprietary, they are black box, some of which are also open source, but they're so large, you haven't really explored the whole realm of how brittle these are to certain prompts that can manipulate its behavior. So the advent of this competition is basically to understand when you have prompts that are trying to prompt inject. That's also a new term that came about, I think, in 2023. So prompt injections are prompts that is basically designed to manipulate uh, uh, the behavior of a large language model or an application that is based on a large language model. And since it's a new concept, you don't have data sets, you don't have a lot of information of how much vulnerable or how vulnerable these systems are, these large language model based applications are to different kind of prompts. And I think the goal was to understand that surface of what exactly that harm could be, or what exactly the level of or severity of the brittleness could be. And once you have all these different teams working together, trying to break each other's um, applications or chatbots by just using prompts, you would get a sense of or you would understand different patterns of prompting techniques that can break the large language model based systems. And I think this competition just allowed everyone to do that.
As a follow-up question to that, do we have a clear view of how large the space of vulnerabilities are to prompt injection? So there are different kinds of things that you could do with prompt injection. We'll get to the particulars of the competition in a second, but it's not just about extracting confidential information, right? You could also manipulate a system to do certain actions that it wasn't intended to do. Do we have that space of potential manipulations or potential vulnerabilities conceptually outlined, or is that still being sort of mapped out at the moment?
So this paper does not. So this paper is a attempt to understand or explore that, but it's very scoped to a chatbot scenario, right? But I I'm in Microsoft. I work in a team that does responsible AI, and we do look at it from different lenses. There is a lot of research around like prompt injections, which can be direct, like you're just using the prompts from the user surface level or the first interaction level to break into the system. There could be indirect prompt injections where you hide these attacks in like some sort of like contextual or grounding data, like documents or like anything that is being retrieved as context for the model to reason on. Or there could be like other mediums of like encoding these attacks, right now we're talking about text, but these could also be visual. So there are, I think, like there's a whole slew of different sort of attacks that can manifest. And but this paper or this competition was very focused and scoped to text based attacks in a chat scenario, which is like a multi-tone setting.
Yes, that's understood. And I want to get to that point as well. I just tried to put the capture the flag setting that we're going to be speaking about
Yeah.
into the context of the potential attacks that are out there. So you elaborated now on, I think, the different kinds of inputs that you could generate to the model, but still manipulating it in the sense that you would extract
Yeah.
confidential information.
Yeah.
But you could also think about the output of such a manipulation, right? It's not only about extracting information that's labeled classified, but you could also get the system to do certain activities that you don't want. And what I was wondering is if there's a good categorization of the types of manipulations that these systems are susceptible to. So giving up confidential information would be one example. Another example might, for example, be if there's some control function that this LLM would sort of be connected to, that you could manipulate that. Do we have a clearly mapped out set of categories for ways that LLMs can be manipulated in one way or another, or is that still a space that we're trying to map out?
I think it's still a space that we're trying to map out, and that's because of several reasons, right? One, the models are also changing. Like even with OpenAI, there are a few updates that are being pushed out. So every time there's a new update, you can imagine that the developers are also trying to like fine tune the model to not react to certain scenarios. But the taxonomy of like what exactly can be a harm is still an open space that is being researched on, but is not clearly like it's not exhaustive. That's how I would say it. Because yeah, it could be misinformation, it could be content harms. Like you could generate something like very sexually explicit because you have tricked the model to like respond in that manner. It could take actions on your behalf depending on like what kind of tools the application itself is like connected with. So it's a lot of possibilities, and I think like the possibilities are also endless because we are still discovering how we are using these models. So the more you integrate into different surfaces, the more vulnerabilities you will discover of how things can change over time.
Yes, fully agree. So let's focus on the particulars of the competition itself. So it was a capture the flag competition. What does that mean more concretely? So what were you trying to do?
So capture the flag basically means that there's a secret which we defined in the competition. This is a 6-character secret that is hidden somewhere in the prompt. And the whole point of this competition is there's going to be defenses that you create to like make sure that when someone is trying to like prompt inject your system, this secret is not revealed. And that's what we call the flag. And there are two phases to this competition. One was the defense phase where you like every team is tasked to like create a defense using prompting techniques. So you prompt engineer or you use like a Python function to basically defend the secret against any sort of leakage for whatever number of like attacks it is facing. And then there's the attack phase where all teams are also trying to like break into each other's systems because you want to extract that secret. And if you are able to like either attack all the teams defenses and you're able to break it, then you win the competition. And that's how the teams actually got awarded for the number of times someone wasn't able to like break into your system, or for the number of times someone was able to like break into your system.
I want to focus a little bit more on the two phases and also the kind of solutions that the teams came up with. So we have the defensive phase and the attack phase. I'm sharing on the screen now the teams that were most effective when it comes to defenses. And one thing that I would like to discuss first of all is these 3 different layers of defense that the teams are able to specify. So as far as I understood, everyone was working with a user interface
Yeah.
that was sort of hooked up to this LLM,
Yeah.
and it offered you the possibility to alter these three
Mm-hmm.
parameters, if you will. Would you mind introducing what these are and why they're relevant for defending the LLM?
So, I think one thing I want to mention before we go into the specifics is each team was trying out different techniques. So, the things that you see over here is like the most effective defenses. So, within each team, everyone found like certain patterns across the number of trials that they had. And so, for example, the system prompt is the prompt that basically encodes the secret, and it tries to prevent the secret from being leaked. So the defense here talks about like how you can like do certain manipulations within the system prompt or the instructions within that prompt to make sure the secret accidentally does not leak. The Python function is basically like one more way of like checking. It could be like, you can imagine like there's a rejects function that checks whether there was an explicit attempt for the secret to be leaked and the secret is has leaked. But then you have this filter, which is a Python based function that tries to like make sure that if it detects that secret, it will instead try to like respond with a different answer, like sorry, we cannot talk about this, like something like on those lines. And there's also like the other section where it talks about like there were two different kinds of models that we are testing on, like there was llama as well as like GPT. And there is a different level of defense that is ingrained in these models. That's what I was mentioning earlier about how different models are tuned to respond to attacks differently. And that's what this defense talks about, like how your setting might be different for like different models. So there's a LLM bias there.
Mm-hmm. And do you think this list is exhaustive in the sense of what you could potentially put in place, like what defenses you could potentially put in place? So thinking about this, like one example that came to mind for me reading the paper is, imagine that you have a response from the LLM that sort of you do a cosine distance, an encoded cosine distance to the protected phrase, so that if these are similar syntactically, not just literally, then you could potentially reject the prompt. Could you, in theory, introduce something like that with this level of flexibility, or would you need
So
more access to the system?
yeah, I think there were also certain rules within the within the competition. Like you couldn't use a lot of semantic filters. What you just described about cosine similarities, just checking for other variations, right? So there were rules
Yeah.
like that we couldn't use. But in reality, when you're thinking about these sort of like attacks and things you're protecting as proprietary or IP information, you could definitely think about like using settings like that.
Mm-hmm. Yeah, because I guess it will become more transparent, or at least my take on this will become more transparent as we go through some of the examples. So maybe we can do that. Do you have off the top of your head like a good conceptual understanding for the top defense strategies? Let's say, do you have some recurring themes? Because I don't want to go through literally like
Yeah.
the literals of each suggestion, but just your main takeaways from looking at the winning strategies
Yeah,
in
so
terms
I
of
think like
defense.
there are three teams who won in the defense category, right? So just going through their approaches, I would say there's no one setting. Like you cannot depend on one method or approach to defend against your secret. It has to be layered, and that's what the main finding is. Like, if you just rely on having the defense, or sorry, the secret being protected by the prompts, there are cases where it leaked. But if you add that Python filter like as a layer to defend, because there could be chances of leakage from the LLM itself, because it's stochastic, then the chances of with having the Python filter, the chances of the end-to-end attack actually being successful and leaking the secret even decreases further, because now you have a defense, like layered defense. So I think that is like the main takeaway from some of these defense categories, because one simple approach doesn't work. I would say that is the main takeaway.
Mhm. Okay. So I think there are more things to say, but I think it'll be interesting to look at the attack strategies as well to get a like an understanding for what people were doing to try and gather that information from the LLM. Would you mind elaborating on how people, generally speaking, approached the
Yeah.
attacks?
So I think there are a few key takeaways for the attack phase, and this is where like my team won in the second position. Um, so in the attack phase, what we discovered was if you trick the large language model, even with it having layered defenses, right? Like the prompt itself plus the Python filter. If you trick into having a conversation where you're starting off with something very benign, like, hey, create this Python function for me, which is going to execute, suppose like a web crawler, and then you start like asking it more detailed questions about revealing the secret itself. Uh, that strategy of starting off with benign responses and then going into more details in a multi-turn fashion is like a very successful attack. And I think this has to do something with how the model itself remembers context of conversation history, and there's a recency bias in what it remembers, and exploiting that really leads to successful attacks. That was one of the key findings. The other finding is also just like making the model output the secret in a format that other layer defenses cannot detect. Like for example, when I talked about the Python based filter, suppose it's catching a rejects match, right? uh, if I force the LLM to output the secret itself, not as the string that it was embedded in, but like breaking off the string as separate characters, and each character has a certain like a word associated with it. So that's the format we're requesting from the model. That is also a very successful attack. So there are like a few nuanced ways of like tricking the model to behave differently that becomes a very successful attack in these different approaches, in my opinion.
Hmm. Would it be fair to map those directly to the kind of defenses that exist here? The point I'm coming from is the defense prompt, for example. It seems like starting off with benign questions would be a way to explicitly target the defense prompt and try to get around that. Because I would assume that the defense prompt is designed like, I mean, this varies across the teams, of course, but in general, I would guess that the defense prompt is designed to prevent the LLM from wanting to give out that information in general.
Yeah.
And do you see the benign starting point as a particular strategy to get around, or as a strategy to particularly get around this defense layer? Because I think the other two, the Python filter and the LLM filter, I don't see how they're necessarily related to the starting point of the conversation. If you have a Python filter, like trying to filter out responses, it seems to me like that would be agnostic to whether, like, to whatever conversation history you had before the secret became or like got shared.
So the way the competition was laid out was everyone was asked to create defense prompts and submit the defenses, and you could also red team, right? Like, which means that you can try to break your own defenses to see whether it's working or not, and that's how everyone
Mm-hmm.
created the defenses. But when we created those defenses, the other teams weren't aware of like what the other defenses were. So everyone was it was almost like a two fold blind review of not knowing what the defenses are, and you try to be creative with your attacks to see how many of these defenses you can break. So these defenses were, I would say, not really mapped to the attack vectors when the attacks were being created, because they were built in a separate phase where it's in a complete blinded mode. So yes, like that I think like that is, there's a disconnect between like the defenses itself and the attacks itself, which makes the attacks successful. Now if in
Mm-hmm.
reality, when you're thinking about using the defenses or the mechanism proposed over here for your application, yes, you can look into the attacks to like amp up your defenses, and like having the prompt structured in a way that it would be able to like even detect like the conversation is straying from being benign to being more adversarial. So that you could have like more prompt engineering or prompt instructions that could prevent that sort of effect.
Yeah, I get your point. I agree that you would create these in isolation so there's not a one-to-one mapping. I'm trying to wrap my hand around the conceptual reason for that strategy being so effective. So, in spite of these being developed in silo, there nevertheless comes a point where you, well, approach the model with a form of attack, and either it's successful or it's not. And it seems like starting off in a benign way and becoming more adversarial over time is an effective strategy. And I don't see how it would be from the perspective of having a Python filter and an LLM filter. So my question is more about, is it like the reason for the effectiveness of that attack? Is it particularly because it is effective against the defense prompt?
Yeah, so imagine this, like in a defense prompt, you're basically telling, and the defense prompt is also limited to a certain number of characters, right? Like that was also part of the competition. It is
Mm-hmm.
basically tuned to protect a secret of 6 characters. But in reality, when you're like having a conversation with the bot, and the system prompt is just tuned to like protect against a secret, and you're asking questions about, suppose, like designing a web crawler or solving a math problem, it's not responding to, or like the LLM is not responding to like generate generate the secret itself or like leak the secret itself. So the filters won't work, and slowly as you build up more conversation in the history, you are basically attaching more and more the parts of the history to the prompt. So the LLM biases itself towards having a more recent view of the history and not knowing what was the previous instructions in the system prompt. So there is a recency bias from the conversation history that tricks the LLM into believing that, hey, like this is nowhere um, a leakage of the exact secret that we wanted to leak, so let's just output this. So that's how the LLM filter fails, right? For the Python filter to fail, it's more about like having a different formatting or a nuanced formatting, that any sort of like matching, either lexical, I don't think there were any semantic matchings because of the competition rules, so the lexical matching is not able to detect that.
Mm-hmm. Do you know if there's a way to encode, for security reasons, particular queries in an LLM or particular prompts to an LLM on a privileged basis so that they're always sort of top of mind for the LLM? Do you know if there's been any investigations along those directions?
So in the competition, we did try with like encoding the attacks to allow this uh, prompt to leak, because what happens is when you encode it in, suppose, like base 64 as an encoding vector, sometimes the tokenizer of these large language models aren't able to perceive what the information was that was being consumed by the large language models, right? Because ultimately at the end of the day, these models are only consuming numbers. So the tokenizers fail at understanding like some of these different mechanisms of encoding. And I think from the attack side, it is a really useful mechanism of just like forcing the model to like generate outputs that it should not. From the defense side, we weren't allowed to like encode because that was part of the competition rules, and we had to like just stick to like using English as the language of like having the system prompt built.
Mm-hmm. In the attack phase, how did it concretely work? Did you have an automated, or like, did you have a predefined set of attacks that would be automatically run on the counterpart's LLM, or did you have the ability during the attack phase to alter your strategies over time?
We did have the flexibility to alter the attacks during the attack phase, and I think it was mostly about being creative. Like you have a limited set of like interactions per day that you can have with the model. So it's based on a time period that you can have interactions of a certain number, like say suppose 60 with the model, and you just keep trying different methods of like breaking the defenses of the counterparts to see which one works. And based on that, you can imagine like you are only looking into the ones which are like mostly successful or partially successful to add on and build more creative attacks. That's how the red teaming or the attack phase process worked.
Hmm. Yes, because I could imagine if you're on an attacking team,
Yeah,
if these filters are not sophisticated or not sufficiently sophisticated, you could start to see through what the other team has actually
yeah.
implemented. Is that something you observed as well from the
Yes,
competition that
there
you
were
could? Yeah.
cases where the meta prompt also, or the system prompt also leaked. So you could very well imagine that you did have a end-to-end overview of like what exactly the instructions were that were baked into the defenses.
Right.
But for most cases, um, that was not the case. For most counterparts, that was not the case. I think because the defenders were also very creative, and they understood that we they could use the Python filter uh, to its most potential, and basically not allow any sort of like uh, leakage into just also like revealing what exactly the instructions are that are protecting the secret.
Mm-hmm. Okay, so that was handled mainly with the Python filter
Yes. Yeah.
among most participants.
Yeah.
Do you have a view? So partly it's that, right? Like that's the most severe breach. If you have really a leakage of the prompt, or not the most severe breach, but a severe breach if you have a leakage of the prompt itself, because then the adversarial team knows exactly what the system has been instructed with. You could also maybe see through like parts of what the LLM is aiming to do just based on interactive feedback. So
Yeah.
you might not have the actual prompt, but if the LLM is instructed to answer in a specific way, it might
Yeah.
become obvious anyway. Do you have a view on how the best prompts were crafted to not like reveal to not leave too much of a trace?
Um, this is something that I would love to like go and look back into, because I don't remember the exact details, but the dataset is available on Hugging Face. Like all defense
Mm-hmm.
prompts and all attack prompts were released. I would say like it was mostly about uh, just making sure that one like if there is like one of the most interesting prompts that I saw was, if someone is trying to like leak the secret or like force the secret out, instead of leaking that, create like just respond with like a more benign sentence which is not even related to the secret. So there were prompts like that made sure that even within the LLM system prompt there was a deceiving response ready to be given out whenever someone tries to leak it, which I think was very creative.
Mm-hmm. Okay. There's a couple of tables, or there are a couple of tables in the paper as well, that we could have a look at with some of the numbers regarding this. So it looks at the, let's say, success rate, etc., of of different scenarios.
Mm-hmm.
One thing that struck me when I read this or looked at this was, partly that a lot of conversations here actually have some success rate even after 7 iterations back and forth. You already gave one account for why this is. So you would start a benign conversation, become more adversarial over time, and that tends to break down the model. Was that across the board kind of the strategy that worked for multiple messages being sent, or is there also are there also other reasons why having a longer conversation history is actually beneficial?
um I think that the pattern we discussed about like having a multi-tone conversation starting off with more benign setting to just trick the LLM is a pattern that was seen uh, across a lot of attacks. And I think like I said, this has to do with like how much the model actually remembers in the end, or to follow system instructions while also remembering what the conversation history was. Because if you keep referring back to the conversation history in your follow-up prompt, usually like it will try to like decide between like, oh, like should I read this into more detail, like what exactly was discussed in the past to have a more like a more concise answer, or should you like also look into more of the system prompt. So like it gets appended in a way in the memory, which kind of like tricks the model to behave differently. That would be, I think, a common pattern that we saw across all conversations. And I think the other pattern we saw even with like multi-turn conversations was the fact that if you try to keep responses concise, like if you force the model to say like at no matter what happens you have to like respond in 20 words, or like I'm making this up, but like the number was much smaller, um, then it also tries to like be like the success of being um or like just defying all these safety alignment policies is like higher, as it tries to like be more concise, because it's trying to like give you the most detailed the most relevant form from the answer, the response that it's generating or reasoning over. And I think that was also like one of the most successful attempts through the multi-turn conversation setting.
Okay. Let's focus a little bit on the data set you created as well. So you, as you alluded to before, you have this data set from the competition that you made available on Hugging Face. What's the kind of structure around that? Is it like the idea, I guess, is for people in the future to use for developing their own defense strategies or just knowing, sort of advancing the field in one way or another.
Yeah.
How is that data set structured? So you have them a few different conversation histories, and then all the individual messages are sort of tied in, I guess, consecutive order in that.
Yeah, there's also like there are labels about that just indicates whether it was a defense or an attack. That's also part of the data set. And I think in total there are like, with all defenses and all attacks conversation combined, they're like 137,000 rows. So it's a pretty large data set. Like if you want to like just filter out by defenses or just filter out by conversations to understand what were the attacks and what were the defenses and tune your own model, you probably can do that.
Mm-hmm. How many teams were actually participating? Like a
There
rough
were
estimate of how many?
43 teams participating in this for both
Mm-hmm.
attack and defense phase.
Mm-hmm. Is your view that having 43 teams gave an exhaustive repertoire of what you can do with these different parameters? So we have 3 defense parameters to play around with that we discussed before. Do you feel like you kind of got the whole spectrum of defenses and that there was a lot of repetition between the teams and what they managed to come up with? Or in those 40 teams, did you find that there was still a lot of variability between the solutions that people came up with? I'm trying to understand how large of a set of participants you would really need before you feel confident that you sort of outline the best defense strategies and attack strategies if you taking the freedom that you had into account.
Yeah, so I think that's a really good question. I would say, given that this competition was motivated by a really big cash prize money, and also it was reputed as it was associated with IEEE Secure and Trustworthy Machine Learning Conference, the teams who participated, I think there were like 144 teams that registered, and 43 actually participated, and like in both defense and attack phases. Um, People participating in this competition were thinking very creatively, and it is important to know that the set of rules were also like scoped down for a 3-month long competition that is based off on like 2 models that is providing these conversations, right? So I think, given at that level of scoped competition, it does feel like it was a very exhaustive one, where everyone tried really hard to like break each other's defenses as well as create defenses that can be protected across all scenarios.
Mm-hmm. Okay. If I would ask you to pick apart this study or to name some of the things that are not as representative as they could be of actual threats that are out there, or like gaps for people that would take the study at face value and say that these are the risks that we need to cover against, do you have any such limitations?
So this is just having the rules of the competition back at the back of my head, right? I
Mm-hmm.
think, from my perspective, the model consumes numbers, which are the tokenized version of the natural language, and in that transformation process, a lot could be manipulated, which I don't think like we the competition exhaustively explores. So just limiting it to English also made sure that we are not trying out these low resource languages that can possibly jailbreak more conversations and more conversational bots, right? That was one part of the setting. Not encoding some of the defenses, or not allowing to encode some of the defenses. That's the other part that could be explored a little bit more, because all of these techniques, like having a different language, having a different encoding, at least for like the text based LLMs or large language models, small language models, or language models in general, and the way things are tokenized, that could manipulate a lot of defense prompts, in my opinion, which I think is still an understudied area, and more competitions could host things around those subjects to have more creative defenses or explore it more creatively.
Hmm. Do you have some examples? So let's say we would create a new study or a new competition.
Mm-hmm.
What kind of additional creativity do you think would be most pressing to
I
allow?
Yeah, I would one, I would really like to have a larger like have the scope of having more detailed system prompts, and not limiting it to like certain number of characters or certain number of words. That would be my first um, change from this competition, just to allow like, hey, if you have even within the prompt you have like multiple instructions that is preventing the leakage, how successful are you uh, for the same sort of attacks. That could be like one area of study. The other, like I mentioned, would be like different mediums of just attacking. Could be in different languages, could be with different encodings. uh, I think the upcoming area in general for a lot of like productivity applications, as well as like any sort of like um, large model based applications is vision. So having the defenses or the attacks also cater to things that can be hidden in images would be and also an interesting area that can be studied for like a different competition.
Hmm. Do you know from an industry point of view particular vulnerabilities that these systems have right now that you think are urgent to address? So, I mean, prompt injection might be one, but like more specifically, do you know if there are certain issues that tend to pop up amongst people that have adopted chatbots, for example, that, yeah, are burning issues, so to speak?
I mean, there are cases of we're looking into security, but there are cases where I think one of Microsoft's competitors, chatbot, was creating a lot of bad images, like things that were forcefully trying to mitigate racial bias. I think Gemini was that chatbot, and it was just creating a lot of bad images. So um, there are areas which are not just security related but also content harms related, which are still uh, an issue. But I think
Hmm.
from what I've seen, because this news is also like 3 months old now, um, there are a lot of rapid studies and solutions that are being released across the board from different companies, especially like even the foundational model developers. They are trying to tune the models as part of their RLHF efforts and fine tuning efforts to make sure that these don't produce harmful content. So I think the scope of vulnerabilities is expanding as new applications and uh, surfaces for integration of these models are coming up. But there's also a very rapid growth in the actual industry leading a lot of like defense approaches or defense research, not just academia. So which is very interesting to see. So I'll say like I don't know how things pan out, but it'll be interesting to see what happens in the later half of 2024.
Hmm. Okay, very good. From your perspective now, were there any key takeaways from this competition in general that we haven't touched upon yet that you think are important to highlight?
Um, not really, but I think like one thing that I would love to mention about like the multi-tone conversation setting is it's interesting that there's actually a certain number of conversations you need to have when you start off with like a benign prompt, or even having like a slightly adversarial conversation with the model, and you're trying to leak the the secret, right? For us, we saw it was like around 4 to 6 tones that you need. But from my perspective, I think it's important to also explore that aspect, because um, it might vary from model to model. Like Llama might have a certain number of conversations, GPT-4 might have a certain number of conversations for which it's tuned to forget things before that threshold is hit, right? So even exploring that in a more detailed manner would be like a good research endpoint.
Hmm. Okay. Do you know of anyone that tried to have dual applications of LLMs being applied to prevent this kind of information leakage? What I'm thinking about in particular is you have the regular LLM getting the prompt, and sometimes it would mess up and it would send out the secret information. You could potentially have a second LLM in the pipeline that feeds off the prompt of the first one and then simply tries to do a detection whether or not this is information that should remain confidential. Do you know if people have tried that, and do you know if so if it's a successful approach?
So not for the scope of this competition, because you only had like one kind of like LLM call that is defending, and the other call that is having a conversation which you use for attacks, right? But there are
Yeah.
researchers, there are research about agents which are actually trying to do defenses in the manner that you described. Like there's a bot that obviously responds, but there's a defending bot that tries to like cover up for any sort of leakages. So I think there are a few papers that have seen on Google Scholar that talks about these approaches. So seems like this is already a researched area that people are looking into.
Mm-hmm. Okay, interesting. From your perspective, to wrap this up, because from my perspective, I think we covered the parts of the paper that I think
Mm-hmm.
we needed to follow up on. So thank you for that. Before I let you go, if there's anything additional you think is worth highlighting, I'm happy to let you do so. Otherwise, we'll close it.
Um, no, not much, but I would say like thank you for having me. It's been pleasure talking about this paper, because it seems like the data set is super useful, but as well as like the findings of this paper were super useful for a lot of communities, because I've had conversations about this to other researchers as well. So but yeah, thank you for reaching out and like highlighting this.